Hello, everyone. Well, one more time, I'm Shamil Biktimirov. I'm from Skoltech Space Center, and this talk will be about the satellite formation flying mission for graphic image demonstration in the sky. And this work actually was made by a group of 3 researchers, and these are also Danilo Ivanov from Kyoto Institute of Applied Mathematics and Dmitry Pritikin from Skoltech Space Center. Let's start. So the talk is actually devoted to distributed space systems. And in general, there are 3 of them. The first one is constellation, and it actually differs from formations and swarms by its orbital configuration. So it's global. It means that the distance between satellites in constellation are comparable to the 7 major axes of the orbits of satellites, and actually each satellite controls its own orbit, so there is no need for controlling relative trajectories between satellites. If we move to formations and swarms, so we speak about smaller distances between satellites, and there is a need to control relative motion between satellites. And in case of formation flying, there is a strict orbital configuration that should be maintained. Well, it should be deployed, maintained, and reconfigured. And if we spoke about swarms, well, it actually should be maintained, but not that strict. So we should keep the satellites in some certain area to satisfy the requirements to the intersatellite distance. And well, there are many applications of distributed space systems, but we selected this one for some reason that I will explain. And this is space advertisement, or this type of formation can be used also for, well, alarms in dangerous situation of citizens, or to illuminate northern regions of the Earth. Well, this application is not kind of a new idea. So there were already some patents and some works published. But, well, we had an industrial project at Skoltech Space Center where the goal was to design a concept for such a mission for space advertisement. And actually, after we did this project, it turned out that, well, it's beautiful benchmark problem for study formation flying missions, control algorithms. And let's move on to the aims of objectives of this work. Well, we study the application of formation flying for graphic image demonstration in the sky. And we use solar sail equipped satellites. These are small satellites. Well, and there are some objectives for this work. Firstly, we develop mission design. It includes procedure for selection target orbit, for designing orbital configurations, and for sizing the orbital reflector, the solar reflector. Then we developed control algorithm for the formation flying mission. It's impulsive, based on impulsive maneuvers, and we validated our methods by numerical simulations. Well, let's move on to the requirements of the image demonstration mission. And since we use the solar reflectors to illuminate regions and with this to project certain graphic images to the point of interest, there are some geometrical constraints for the mission. And of course, the satellite should be lit by the sun in order to reflect the sunlight to a specific point of interest on Earth. And it should be close to nighttime at the point of interest, and we define it by the sun elevation angle. It should be, for example, smaller than -5 degrees for good observation conditions. Then we consider that satellite should be at some elevation angle at the point. Well, in our case, it's above 10 degrees of elevation, and we want the satellite to be bright enough to be distinguished among stars. And we refer here to well-known iridium satellite flares that ranges from -6 to -8 magnitude. Also, there is a requirement for the orbital configuration. And here, the main thing is to put satellites at such distances that they will be distinguished by a naked human eye. So to make the angular distance be greater than 1 arcminute. And let's speak more about spacecraft visibility model. So here is the parametric model, how we calculate the magnitude of reflected sunlight at the point. Well, actually, magnitude is a function of intensity of reflected sunlight, and the reflected sunlight is a function of reflector parameters and geometrical parameters, such as elevation of satellites at the point and incident light angle. Then we consider the following case study to demonstrate what our methodology, our method is, and how do we control the formation. Well, the case study is to make 2 demonstrations above Paris at the date when the anniversary of International Academy of Astronautics will be. So it's 16th of August. And we want to make 2 demos at the same day. The first one will be scheduled for morning time before sunrise, and the second demo will be scheduled for the evening time. And we will define what exactly the time is and what the orbit should we select. The orbit of interest are circular sun-synchronous orbits that lie close to the terminator line. And orbit should ensure that, well, we will see there will be a direct line of sight between Paris and formation satellites at the same lighting conditions. So, for example, you can see the figure and the square and circle, and these are the midpoints of demonstrations. Then we select such an orbit to ensure that satellite will go above Paris at sun elevation angle smaller than -5, and satellite should be above 10 degrees of elevation. And actually, you can see here final orbital parameters that we selected. So the orbit, well, is sun-synchronous orbit, it's circular, and it has altitude of approximately 800 kilometers. Then, to prove that our selected orbit is fine, we calculated the image demonstration parameters or mission demonstration parameters. So as you can see here, well, on the left figures, you can see that sun elevation is not greater than is not smaller than -5. The satellite elevation, well, is greater than 10 degrees. And we considered actually 2 magnitudes of satellites of reflected sunlight. These are magnitudes of -6 and -8, and calculated the area for reflector to ensure this magnitude of reflected sunlight during demonstrations. And well, as you can see here, for example, approximately 20 meters in area reflector, we have always magnitude of the reflected sunlight better than -6. And for 135 square meters, it's better than -8. So we satisfy the mission requirements. Then there is a short animation from STK where we validated that our analytical model for orbit selection is fine. And you can see here the time of the first demonstration. Well, it's a sunrise for Paris. And there is the first demonstration. And then we can see the second demonstration at sunset. Then let's move on to the designing of orbital configuration. We already selected the target orbit. Well, to define the orbital configuration, we should think about relative motion. And for this purpose, let me firstly explain what the orbital reference frame we use. Well, z-axis is aligned with local vertical, x-axis is a long track, and y is normal to the orbital plane of the target orbit. And to explain and to analyze the relative motion, we use linearized equation of relative motion, Hilke-Hesse-Wiltshire equations that have analytical solutions. And these there are solutions that correspond to the closed or periodic relative orbits. And for the purpose of image demonstration mission, we need to have projection of the relative orbit to be circular in the horizontal plane. And for this purpose, we use projected circular orbit type. Then, well, we defined our orbital configuration for both demonstrations. We firstly selected the minimum intersatellite distance. It's about 700 meters and corresponds to the one arc minute at this orbit. Well, and then we built with a minimum possible number of pixels the letters of AA, well, acronyms of Actor Astronautica Journal for the morning demonstration, and logo of International Academy of Astronautics. These are 26 satellites in total, and then we will control these satellites to, well, to establish or deploy these configurations. For the control, we solve this problem. Actually, well, in general, what we can see here, we have a pair of satellites, and we know the state vectors, inertial one. And if we calculate relative state vectors to the orbital reference frame built with respect to the leader satellite or the follower satellite, well, we can see that we have this R small and V small relative position and velocity. And for example, for a pixel, we can predict with solution of Hill-Cohesi-Wilshire equations the required relative trajectory. And it can be converted to the state vector for the required, well, orbit of a satellite. And the goal is to just compensate difference between current and required orbit of a satellite in information. Well, we do it, we correct orbit with the aid of impulsive maneuvers. These are 3 consecutive maneuvers that actually aims at correcting difference in orbital elements. For example, you can see here the performance of these maneuvers. So we had some deltas in each orbital element, and we corrected it to be as small as possible with the aid of impulsive maneuvers. Then we also thought about optimal reconfiguration to prolong lifetime of formation. So the idea is that at different orbits, satellites spend different amount of fuel because, well, these solutions, the closed periodic solutions of Hill-Cohesi-Wilshire equations, they are obtained with linearized equations, and there are also some perturbations, and therefore we should spend some fuel to correct the relative trajectories. And the farther from the origin of the reference frame the satellite is, the small amount, the bigger amount of fuel the satellite spends for the orbit correction. And therefore we solve such a problem when we reconfigure orbital configurations, which goal is to maximize minimum amount of fuel among satellites and to minimize total spent fuel for the reconfiguration. And this is made with the aid of assignment problem. Then, well, coming to the numerical study, well, the dynamics was studied in inertial reference frame, and we took into account only J2 perturbations because of the altitude of the orbit, so it's 800 kilometers. And well, here is the equation that we use, and here is the mission timeline that was designed in mission design study. Well, we know when should we start reconfiguration, when is demonstrations, and when we should reconfigure our previous orbital configuration. And these are the, let's say, final results of what we achieved. Well, this is the orbital configuration and relative trajectories of each satellite after the deployment stage, which took about 3 hours. And this is how the position error was changed during the deployment procedure. So finally, we reached, after deployment stage, well, accuracy of 30 meters or position error of 30 meters. This corresponds to the reconfiguration stage. Well, you can see that logo of International Academy of Astronautics, and well, here are the position error during reconfiguration. And finally, you can see how it looks like in animation. So now the first orbital configuration is deployed, then time for reconfiguration came, and now the satellites, which are black, should reach the red required trajectory or state vectors in orbital reference frame. And now you can see that they start reconfiguration at some moment after the first demonstration, and it reached the second orbital configuration. So finally, to conclude, well, we developed a mission design method for this application of formation flying. And well, we also developed control algorithms which are impulsive and allows us to deploy, maintain, and reconfigure satellite formations. And actually, well, the further plans, we would like to improve the accuracy of the relative motion control algorithms by adding the continuous control for relative orbit maintenance. And that is actually it. Thank you very much for your attention. Probably there is a time for a couple of questions. We have a question for Shamil regarding his presentation on space advertisement. Well, here is a question about are you aiming at consistent reflected sunlight intensity from every satellite in the constellation, or there is a provision for variable reflected intensity, such as from different angled reflectors or different satellite attitudes? Well, actually, I did not understand fully the question, but well, now the strategy is the following. We, by mission design procedure and solar reflector sizing, we would like to ensure that for a whole demonstration, the magnitude of reflected sunlight will be better than some value. For example, it's better than -6. But well, it will grow with the time because of different geometrical conditions. Of course, we can use some materials that can change reflectivity, and we can keep the magnitude of satellite with some specific value. It's also possible. Yeah, but now we don't plan for this. Maybe you can clarify, or did I answer your question? Okay, thank you. And one more question about the presentation. It's about the practical applications of the technology. Well, yes, of course, there are huge number of applications for formation flying missions, and even for formation flying missions with solar reflectors. If we speak about solar reflectors, the first idea was proposed by Hermann Oberth, who proposed to use it to generate power on Earth. Then it was proposed by Soviet Union to illuminate northern regions like Murmansk, where they have lack of sunlight at some seasons. And yeah, you can well, notify people in some situations, in dangerous situations, for example. Then if we talk about formations in general, there are huge amount of applications that can't be well made without formation flying. We need to have a distributed system of multiple satellites in strict orbital configuration. For example, well, the most interesting are the spaceborne telescopes for well, distant stars observation and so on, or distributed radars. Such experiments were already made, and some systems for precise measurements of different Earth parameters like gravity field potential measurement or magnetic field measurement, well, and so on.